back at you, Dave. Coming back to, I got to pause it so we can play some more Thunderstruck by the great AC/DC at the end. Okay, change of base. This is saying that for any logarithm of the form log base b of a, we can rewrite the logarithm in this manner as the division of two logs, where I take the logarithm of a over the logarithm of b, and I can make it any base that I want. So that C stands for any single base. Yes, anything that is convenient for me. It is quite handy. Very nice proof here. We can talk about that in class. And also the change of base is here on your formula sheet. So that's good news for us. All right. Let's take a look, see how it works. And this is really just showing you that change of base is legit. It's not a formal proof. It's just a bit of convincing you by rewriting it and showing it it's all the same. So find log base 2 of 9 equal to x. Okay, so, well, that's pretty easy, right? We rewrite it in an exponential form. 2 to the x equals 9, right? A equals that. Then we can take the log of both sides. Log 2 to the x equals log 9. X log 2 equals log 9. And then we take x equals log 9 over log 2. And we'll crank that on our calculator. So I'm going to do log 9 divided by log 2. And I get about 3.169 blah, 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 blah to 3 sig figs. That would be 3.17. Then they're saying, well, why can't you just do this by changing the base to 10? Let's go back. Let's grab this, copy it, move it over so we can follow it. Okay, so there's our change of base right here. And so for b, we're going to change log base 2 of 9 to, okay, so log base b of a, so that's going to be a log 9 on top and a log 2 on the bottom. So I can rewrite that as log base 10 of 9 over log base 10 of 2. But remember, I don't have to write the 10s because if there's no base there, we assume it's 10. And that's the exact same thing as this. Log base 9 divided by log base 2 is the same as this, so we would get the same result. Well, what about changing it to base e? Would we still get the same result? Log base 2 of 9. So log 9 over log 2 using change of base rule. And so that would be a base of e. Base of e. Wait, hold the phone, Chuck. Don't we have special notation for logarithms with base e? We certainly do. So all we would have to do is do natural log. Oh my gosh, I was supposed to write 2 there. So sorry for the confusion. And natural log here. So let's see how that turns out. We'll do natural log 9 divided by natural log 2. Bam. Holy smokies. It is the exact same thing. So there we go. We've shown you that. Just some examples of why, or that you can indeed do the change of base. Okay, so now we're going to solve for x exactly. And what are we going to do here? So we can rewrite this. 8 to the x we can rewrite as 2 to the 3x because 8 is 2 cubed minus 5 times 2 to the 2x. And that's equal to 0. 4 is 2 squared, so that's why I can do that. Then I can factor out a 2 to the 2x, and I'm left with 2 to the x minus 5 equals 0. So then I get 2 to the 2x equals 0. And let's see, 2 to the x would be equal to 5. This is impossible. I can't raise anything to a power and get it to be equal to 0. So I can rewrite this in exponential form, right? And say x is equal to log base 2 of 5, 2 to the x equals 5, which is a perfectly good answer, but it might be that I want to write that with a different base. So I can write it as log 5 over log 2, or log base 7 of 5 over log base 7 of 2 if I needed to, or even natural log of 5 over natural log of 2. And that is according to our change of base law. All right, let's get into some graphs here. The general exponential function f of x equal to a over x, okay? The graph of a to the x looks like this when a is a fraction, okay? And when it's not a fraction, it goes up. Usually you're used to seeing this like go up real quickly. I wish this drawing was better. I apologize for that. But it's the graph of an exponential function. And the horizontal asymptote is y equals 0, the x-axis. We know that. Okay? The inverse function of y equals a to the x is x equals a to the y. And in logarithmic form, y is equal to log base a of x. So what that tells us is if we have f of x is equal to a to the x, then its inverse is log base a of x. Get it? Because x equals a to the y, which is equivalent to this. So the inverse of a to the x is log base a of x, which is tremendous news because if I have a function and its inverse, the domain of the function is the range of the inverse. See? X is an element of the reals, y is an element of the reals for log of x. Y is greater than 0, x is greater than 0. And the horizontal axis goes from y equals 0 to x equals 0. So this is the one we're used to, y equals a to the x. So the logarithm looks like this as long as a is greater than 1. But if a is between 0 and 1, which is rare, then it's going to look like this. Okay, you can see that makes it worse. This is a mirror image of y equals a to the x when a is between 0 and 1. And the vertical asymptote, looky, is x equals 0 for both instances because the vertical asymptote for the original function is y equals 0 or the x-axis. So let's just do a couple of graphs. All right, so we're going to consider the function f of x equals log base 2 of x minus 1 plus 1. But let's just do a quick reminder here. We know that the basic sketch of a logarithmic graph looks like this, and we have a vertical asymptote of x equals 0, and this goes down to infinity, and this goes to negative infinity, and this rises to positive infinity. So that's going to help us with the domain and range. So the domain, it's going to help us a little bit. The domain, what we have to worry about with logarithms is that we can only have the, find the logarithm of a positive number. So inside, x minus 1 must be greater than 0. So that means x must be greater than 1. And the range, the graph helps us with because this goes down forever, this rises up forever, so it is an element, oops, I put x, y is an element of all real numbers. Part B, find any asymptotes and axes intercept. So let's talk asymptote, okay? So the asymptote right now is x equals 0. But as we have learned, okay, with this minus 1, inside the parentheses, the graph of your basic log base 2 of x, let's say that was log base 2 of x, is going to move to the right 1 unit, which means the horizontal asymptote is also going to be, the vertical asymptote is also going to move 1 place to the right. So the vertical asymptote is x equals 1 because of the shift. Without anything in here, it would just be x equals 0. So the vertical asymptote is always controlled by whether or not we're adding to or subtracting from x before adding within the parentheses of the argument, if it's part of the argument. Okay? And then there's no vertical asymptote. So when axes intercept, there's clearly not a y-intercept, but to find an x-intercept, okay, remember, I let y equals 0 and solve for x. So I have 0 equals log base 2 of x minus 1 plus 1. I subtract 1, and that is equal to log base 2 of x minus 1. Going exponential, 2 to the negative 1 equals x minus 1. So then 1/2 is equal to x minus 1. So x is equal to 1 1/2, which is 3/2. Bam! Okay? So we can use all that to sketch this graph. Let me put a graph on here, maybe make it a little easier. Okay? So I know that the domain is x greater than 1, and I have a horizontal asymptote at 1. So let's go ahead and put that in there as best we can. Oops. So this is x equals 1. I have an intercept at 1.5 right there, and I know this goes down to -infinity, and it keeps going up this way. And so it's going to look something like that, okay? You can also, if you want to try and get a couple of points, that's fine. Like the point, if I can get, if I can get the logarithm equal to 1, like log base 2 of 1 is equal to 0, and that's going to happen when x is 2. 2 minus 1 is 1. Log base 2 of 1 is 0, plus 1 is 1. So I could have done a little bit better of a job and plotted that point as well. Okay? So now D, they want us to find the inverse. Okay? Well, we have y equals log base 2 of x minus 1 plus 1. So that's for f right there. So for the inverse, we switch. X equals log base 2 of y minus 1 plus 1. And we are going to subtract 1 from both sides. X minus 1 equals log base 2 of y minus 1. We're going to go exponential. 2 to the x minus 1 is equal to y minus 1. So 2 to the x minus 1, add 1 to both sides, plus 1 equals y. So our inverse function is equal to 2 to the x minus 1 plus 1. Okay, and that looks, if you think about it, here's my base, here's my base, here's my logarithm, here's my logarithm right here, and or my argument, I should say. So it all works out nicely. We also know that the domain of this function is all real numbers. There's no value of x that I cannot put in, okay? And so that's the domain, which is the range of the original function. And as far as the range is concerned with the exponential function, it's going to be y greater than 1, because, again, we have, an exponential function looks like this, okay? And since it's an exponential function, remember, right here is the basic shape, and usually an exponential function all by itself intersects the y-axis at 1 and has a horizontal asymptote of 0, so it's y greater than 0. But this vertical shift moves it up, which makes the range y greater than 1. Which corresponds with the domain of the original function, which is x greater than 1. All right, that is all I have for now. Hope you enjoyed it.